Now it's my honor to introduce today's speaker, Mr. John Gustafson, a pioneer in reimagining how computers handle numbers. Dr. Gustafson is currently a visiting scholar at Arizona State University and chief scientist at VQ Research, where he focuses on energy-efficient computing solutions. Many of you will recognize his work on Gustafson's law, a foundational concept in parallel computing, or his groundbreaking development of cluster computing, which earned him the prestigious Gordon Bell Award. Never one to settle, he spent years challenging traditional approaches, like his revolutionary work on union computing, detailed in his book, The End of Error. Today, he'll share insights into Posit computing, a promising new number format that could redefine energy efficiency in high-performance computing. With decades of experience at institutions like AMD and the National University of Singapore, Dr. Gustafson brings both wisdom and innovation to the critical conversation. Please join me in welcoming Dr. Gustafson. We are eager to hear your thoughts.
Thank you for that kind introduction, and good morning, everyone. Before I switch to the slides and get off camera, I wanted to at least hold this up for everyone, because I always get the question of, yeah, when are we going to see this in real hardware? Well, it's been out for months. You can buy a complete processor stack accelerator for this kind of arithmetic with C, C++, Python, and applications ported from Caligo Technologies. They're selling this right now. And so I wanted to hold that up before I lose control of the camera here. So let me do a share screen. No, first I want to do, no, I have to share screen first. Good. And then I think that works, except I now need to do that. I think that works, right?
That looks great.
All right, that's what I needed. All right, so my thesis, as I think you heard a hint of, is that the slowdown of Moore's law and the needs of AI made us realize that IEEE floating point, which really dates back to Intel 1977, is obsolete. IEEE floats are very wasteful for storage, which means, of course, this also wastes bandwidth. And bandwidth is where most of the energy and power go in a computer these days. It's all in the communication. Now, the Posit format was introduced in 2017 as a new way to compute with real numbers. And unlike floats, they're designed mathematically to meet engineering goals. Gains of 4 times are possible by using fewer bits but getting better answers. So this is like 2 turns of Moore's law. And it is a watershed. I would call it a revolution, and it is well underway. It's being adopted rapidly. So I want to try a different way of explaining it than I've done in previous presentations. There's an old game called 20 Questions that goes back to the 1800s. It was actually a parlor game, but was made into a radio show in the United States, really part of the 20th century. And you identify, someone has a mystery object that they have in mind, like Winston Churchill's cigar or the pen I'm holding in my hand. And the idea is to nail it down in 20 yes-no questions. And notice that yes-no questions are, well, the answers are bits. So let me apply this to just very simple computer arithmetic by saying, I'm thinking of an integer between 1 and 30. Any computer scientist worth his salt should be able to get that in 5 questions. Is it 16 or larger? No. Okay, put a 0 up. Is it 8 or larger? Yes. Okay, now we have a 1. Is it 12 or larger? So this is just divide and conquer. But every single time you ask another question, you're refining, you're splitting the set of numbers that it could be into smaller and smaller pieces. And by the time you get to, well, is it 11? Yes, you win. Now you have a series of no, yes, yes answers. And of course, that's 11 in binary. That's the way integers work. They are very logical. They are very mathematical. And we're all accustomed to this. So it's always kind of a shock to see how far floating point format is from this kind of a concept. It's also how A to D converters work. Analog to digital converters do this kind of refinement of, once you convert a signal, once you get something in the form of a voltage, then you can make voltage comparisons and spit out each bit of the digital version of that voltage. What if the game starts with, I'm thinking of a real number? Well, where do you even start? What should be your strategy? And this is a different way of thinking about how do you want to be able to represent real numbers on a computer with a string of bits. Now, I see this a lot. You cannot represent all the real numbers on a computer because there are an infinite number of them, and computers only have a finite amount of memory. I'm surprised how many people tout this. Somehow it doesn't bother them that there's an infinite number of integers, but it does bother them that there's an infinite number of real numbers. And they say, oh, you can't do it, so you have to settle for something less. This is really a fallacy. On the next slide, I will do it in 3 bits. I will represent all the real numbers with 3 bits. Projective reals are like this. You can wrap the real number line onto a circle, which suddenly looks a whole lot more finite. Imagine a light bulb at the top of that circle projecting points on the circle down onto the negative and positive infinite real line. And you see that, of course, at the very top, it would project to the point at infinity. I'm going to add 1 or 2 concepts to this very old idea of projective reals. It looks like this. On the inside of the circle, I've put 3-bit binary numbers. Their exact values end in 0, but intervals end in 1. And up the top is what I call NAR. N-A-R is not a real. Okay, so a string of zeros just means the number 0. But 001 means all the real numbers between 0 and 1, non-inclusive, and so on. So I can do up to infinity with 011 between 1 and infinity, and every single real number maps to one of these representations. It's not very accurate, but it is a mapping. It's just not a 1-to-1 mapping. So yes, we can't do a 1-to-1 mapping. What if we wanted to add another bit? Well, between 1 and infinity, I could put any number really, but let's for now just choose the number 2. Now notice all the existing numbers I had, that if I add a 0 to them, they don't move. This is like working with decimals. You add a 0 to the end of a decimal, it doesn't change the value. But if you add a 1 to the end of a binary decimal, then it changes the value. It's an in-between value. And so between 1 and 2, I have the open interval 1 to 2 and so on. This is what's called a type 2 unum because the reciprocation and the negation are perfect. All you have to do is flip it horizontally to find the reciprocal of a number, and flip it horizontally to get the negative of a number. So that's rather elegant. We did not have to use 2 at the northwest point. I'll talk more about that later. So reciprocation is as easy as negation. So divide becomes on an equal basis with multiplication. The problem is that actually building hardware for this, you're faced with things that look like table lookup. But this is like interval arithmetic. I'm actually encompassing real numbers. If I round it, so instead of numbers between 2 and infinity, I just say, well, let's pick a number. That would be 4. Between 1 and 2 would be 1.5, 3 halves. Between half and 1, I'll pick the midpoint, 3/4, and so on. So now the reciprocals are not perfect. They're perfect for powers of 2, but not for the in-between parts of a range from a power between integer powers of 2. Once again, appending a 0 doesn't change the represented value, but appending a 1-bit does one of several things. Between nar and x, insert 2x. Between 0 and x, insert half x. Otherwise, you insert the average. And so I can flesh out precision. As you add bits, this grows not only the accuracy, the relative accuracy over near -1 and 1, the east and west side of the circle, but at the top and bottom, it increases the dynamic range at the same time. Contrast that with floating point arithmetic, where you have to disassemble this set of bits and this set of bits and use a different bias and a different offset, and then put it all back together again. It's nothing like that. These are the 4-bit posits, what you see here. And it really starts to look like a number system, barely. Okay, posit is a word in philosophy that means a statement that is made on the assumption that it will prove to be true. I initially thought about calling these guesses because when you're using approximate arithmetic, you're guessing your way through a calculation. But guess sounds kind of pejorative. And some people in numerical analysis didn't like that. So I said, well, let's call it a posit and assume that it's going to work out, that the calculation is going to be okay. I also like the fact that it was 5 letters so that you can change all the word float in your code to posit and it won't change the pagination. Everyone is out of bandwidth. Training ChatGPT cost the US almost it almost was $1 billion in electricity, and most of that electricity was communicating bits from place to place. Anytime you use more precision than you need, you are wasting memory, bandwidth, energy, and power, and you're also wasting time. It could go a lot faster if you could right size the precision. Programmers use excess precision so they don't have to think. They don't know numerical analysis. They probably weren't taught it in their computer science courses. So they just throw 64-bit at everything. Or maybe 64-bit is what's native in the hardware, so it actually runs faster. I know on Intel processors, at least for integer operations, 64-bit integers run faster than 32-bit integers, which takes some getting used to. The current methods we use for representing numbers really date from a time when operations were expensive and moving data was practically free and energy was cheap, dirt cheap. That's not the case anymore. So what if we could get better answers using fewer bits? We can. So posits work like 20 questions except for real values. Is x less than 0? If it is, then you got to start with a 1, which I've shown in red here because it's the sign bit. Is x less than -1, or is x less than 1? That gives you the next bit and helps you home in on what's going on. Finally, you have a choice that says, well, how aggressively would you go after a guess? Is there a person who's likely to think of a really huge number or a really tiny number? At this point, you have to pick a constant c and say, is it less than 1 million? Is it less than 1 millionth? That kind of question. So that's kind of, you can do different strategies for c, but that's where all the different forms of posit arithmetic come from, is what you pick for c and how you do the rest of the yes/no choices. But it's reading from left to right, which means you could build an A to D converter that would take you directly to real numbers instead of taking you to fixed point, even spaced integers. Now, the regime format lets us decode the bit string. And this is not the way that posits were invented. Posits were invented geometrically by looking at that circle. We had to figure out how to decode them, and we realized that there was something like a run length thing going on. Before I explain that, let me mention that the idea of ghost bits. So if you write a decimal like 3.75, you are implying that it's followed by an infinite number of zeros. So I'm going to call the 3.75 explicit digits, and all the zeros that follow are ghost digits. Okay, so let me look at a bit string, and it looks like a kind of a thermometer notation, unary notation. It's the number of things in a row, like clothing sizes. You have large, extra large, extra, extra large, extra, extra, extra large. It's that kind of thing where you keep on building a string. Or if you look at sizes of a tool or a wire size, you might have a size 0, a size 00, a size 000 to go the other direction. But actually, that can represent both negative and positive numbers, unlike just tally marks, where the more marks you have, the more ones in a row, that's the bigger the integer. The regime format is, I think, the first of its kind, because there's a finite number of bits. It's not like Gollum Rice, or it's not like some of the other formats that have existed in the past, like thermometer code, because it has to stop. It has to be terminated by a ghost bit. But that top one, I want to point out, the run length is infinite. If you have 000, then you have an infinite number of zeros. So the integer meaning is an infinitely small number, negative infinity. If you have 2 zeros in a row, that's -2. 1 0 in a row, it's -1. Now, it's a little different when you flip over to the other side. I have to have a 0. So the next one up actually represents 1. It represents 0 if the run length is 1 of a 1 bit. So you take the number of 1 bits in a row, subtract 1, and that's the integer that it represents. That's the regime. So it's like tally marks, but it's signed. Takes some getting used to. Once we had that figured out, then we knew how to actually write a formula from the bits, a little bit like you would decode a floating point number. And here's the formula. You take the value of the sign bit, and that expression 1 minus 3s, that's -2 if s is negative, and 1 if s is positive, that is, it's a 0. So from -2 to 1 is the 2's 1. If you take the 2's complement integer of 1, you get -2. Maybe I'm not making sense. Let me put it this way. On the right-hand side of the circle, you count up from 1 to 2. On the left-hand side of the circle, you count up from -2 to -1. So the implicit value is actually -2 for negative numbers and 1 for positive numbers. For floating point, it's always 1. That hidden bit always represents a 1. Then you add the fraction, and then you multiply it by 2 to the scale. And scale is the value of the sign. Scale is that expression down there, which if you like to say -1 to the power s, I don't like that notation. I'd rather just write 1 minus 2s, but that's just a -1 or a +1 times the regime plus the sign. And that includes the 0 and the top of the circle, the exception. So I don't have exceptions. You get tapered accuracy with this, in that you get more accuracy near 1 and -1. The extreme magnitudes have fewer fraction bits, but I don't need to have exception values in the system. So I call IEEE floats weapons of math destruction. They were designed for 1970s engineering limitations, and they were really ad hoc. They were actually created in Intel for the IBM PC. It was to be a coprocessor called the 8087 that would go in a socket right next to the 8086. And it's an anthropomorphic thing where you say, we use scientific notation of a number with a fraction times 10 to a power. So let's just do it that way, except we'll use this set of bits for the sign bit, and we'll use this set of bits for the exponent. And oh yeah, this exponent needs a sign bit too. And then we'll make special exceptions for all kinds of fancy things like -infinity and infinity. And it just becomes a real grab bag. There is no guarantee in IEEE floats of repeatable or portable behavior. People find this out the hard way because they thought it was a standard. It says so right on the label. It's a standard, but it's not. It's more like a set of recommendations than anything else. Computations change when you parallelize them. And that makes you wonder whether you did a bad job of parallelizing it and it's a bug, or whether it's just rounding error. You can spend hours trying to figure that out. The very low accuracy of 32-bit floats forces everybody to use double precision for high performance computing. It has for decades. But in fact, if you had really good 32-bit number representation, you might not need 64-bit anymore. And that would be a huge savings for, well, for everybody. It's not logical. The IEEE standard says that you can have x not equal to itself. That's when you have a not a number. And a equals b doesn't mean that the function of a equals a function of b. If you have 0 and -0, they actually believe in +0 and -0. And I always say that if you believe in +0 and -0, then your math education has failed you. But there is in the floating point standard. And the reciprocal of -0 is -infinity, but the reciprocal of +0 is +infinity. Yet the standard says that -0 equals +0. Get that. And you can actually test, is it true that +0 is greater than -0? You get yes. And if you test, is -0 greater than +0? You get no. So what are they? It's just the meaning of sign 0 is all over the map as you read through the standard. It is not a mathematical quantity. There's very poor handling of overflow and underflow and not a number. And if you get something that's not a number, it should propagate to the final answer so you know something went wrong. It doesn't always. The dynamic ranges that they picked are really poorly matched to application needs, as I will talk about later. Okay, I always have a hobby of asking people, how do you know your answer is right in scientific computing? And the usual reaction is just laughter, kind of uncomfortable laughter. What do you mean? And sometimes they say, well, we use double precision. Nothing can possibly go wrong, right? Or it's the same answer we've always gotten, or it's the same answer others get. These are not good answers. I use tried and tested software. I trust it. So there's so many things that can go wrong in numerical computations, and people really are ill-equipped to find out if they're doing something, a calculation that's just grossly wrong. And sometimes it can cost lives to actually do these to get rounding errors that you don't know about. It's a serious matter. Just a reminder, I think you all kind of know this in your head, but there's really 3 layers of computing. In the human layer, not only do you have decimal character strings that you can read or write or type in, but you also have light and sound and position of the steering wheel and all the things that could be turned into a number. And that's the compute layer. Compute layer has these finite precision representations using bit strings, and you can see those and print them and program with them. But under that is a math layer where it it imitates infinite precision representation. It computes things as far as it needs to be in order to be able to round it correctly to the compute layer. So if you start with some simple question like 0.1 plus 0.2, you expect to get 0.3, but there's a rounding that just goes into the compute layer because you're using binary representation. So that's some, I don't know, integer divided by 1024. And you can do that exactly in the math layer, and it looks like that. I guess 819 over 2 to the 13th plus 819 over 2 to the 12th. But then after you get that answer as a perfect fraction, you have to round it to get it back to the compute layer. And you might have a finite number of bits, so it turns into 307 over 1024, and that turns into 0.2998 if you're using binary arithmetic. So we expect that 0.1 plus 0.2 equals 0.3, but computers always let us down that way. This is what IEEE 754 looks like in a nutshell. There's 4 exception types, there's 2 zeros, there's 6 rounding modes. The rounding modes are invisible to the user. You have to look in the make file to see if they've been set differently from the standard. So you can get all different answers out of a single piece of code and the same data. It's kind of a mess. I think I got like 6 exceptions to the normal kind of flow. And here's a dirty little secret. Everyone has started throwing the top 6 cases off to software handlers or to some kind of microcode. And it can take like 200 clock cycles to handle anything that's not a normal float on the bottom. So when you say, I have floating point in hardware, they're usually talking about the bottom case only. But a real floating point processor, they're almost extinct. Started in about 2005. It accelerated when the GPUs came out. They always started flushing the subnormal numbers to 0. So you didn't have the same meaning for the bits. If you moved it into a GPU, it turned into a different number. For 16 bit floats, this is 6% of all the bit patterns are in this exception value case. So why care about reproducibility? Cloud computing getting different results on each devalues the computations. If you can get it, send something up to Amazon Web Services and run a climate model, let's say, you get a different answer every time, then it really lowers the value of the computation. And huge scale calculations make reproducibility harder to achieve than ever before, mostly because parallelism taxes the associative property of addition. So what used to be a rare small discrepancy can actually cause a butterfly effect. But you really lose productivity trying to figure out why answers differ from one run to another. Here's an example with climate prediction. The colors indicate the same model being run repeatedly, and you get all different answers all over the map. Now, if you're trying to convince something in a political argument that climate, global warming is a real threat and is very important, and you show them something like this, they say, well, it looks like you can make a computer say anything you want, and it totally devalues the simulation to if you're a person who doesn't want to believe in global warming. The same computer can actually produce irreproducible results, and this is kind of astonishing the first time you see it. But suppose x is 10 to the 160th power and you're using 64-bit floats, and the computer sets y equals x squared in the run. The computer does some other stuff for just a few milliseconds. The computer then calculates z is the square root of y. You'd expect to get x back, right? And you do. You get 10 to the 160th back. Seconds later, you run the same program and you get z equals infinity. That's odd. So you invoke the debugger and you always get z equals infinity. That's called a Heisenbug. You try to look for the bug and it changes the behavior of the bug. There's a 1980s programmer facing a Heisenbug. Now you insert print statements in the code to figure out what's going on. It always prints z equals 10 to the 160th every time. Well, what's going on is that there's an 80-bit register in all x86 processors, Intel and AMD, for the floating point stack. That's from back in the 1977 design of that code processor. And compiler people can't resist using extra registers. So they do all the temporary calculations in this extra precision stack. The 80-bit register does not overflow when you square 10 to the 160th. You get 10 to the 320th. But 10 to the 320th is outside the actual range of 64-bit floats, so it overflows to infinity. So if it's honest, it would actually overflow, but it can't resist just keeping it in that extra precision register. And then when it comes back down, you never know that it actually should have overflowed. But it's weird to be able to run the same program with the same data on the same computer, seconds apart, and get different answers. Here's why linear algebra is importable using floating point arithmetic. Now, these powers of 2 actually aren't that large as numbers go. But if you're just doing a row of a matrix times a column of a matrix to get a single entry there over on the right in the C matrix, these values are all exact in single precision. And in fact, their products are also, the dot product is also exact elements. So you can represent all of these products as perfectly without any rounding error, but you need to now add them. And maybe you use 64-bit double precision thinking that'll make it safe if you're starting with single precision. But parallelization can change the order of summation, even at this small 4x4 matrix level. There are 15 different ways to sum up 4 numbers. And here's what they never taught you in computer science. You can get the value 0, 2, 1, or -1 doing that with 64-bit floats. That's appalling. That's why I say they are weapons of math destruction. You can get 4 different values depending on your summation order. We have just learned to tolerate this, but we shouldn't. We should demand something a lot better. There is no reason that we have to go through life tolerating this kind of junk mathematics. You park your mathematics at the door when you start using floating point arithmetic. So can we fix the IEEE 754 standard, make revisions to it? It gets revised every few years, but all they do really is add different precisions to it. They add different rounding modes to it. They don't want to spoil backward compatibility with everything that's been written so far. Kahn says linguistically legislated exact reproducibility is unenforceable. And faster matrix multiplication is usually too valuable to forgo unneeded exact reproducibility. So I don't think he's going to be of any help. And the solution is to form a new alternative standard that is based on mathematical principles. And I've been told this can't be done. And if an elderly but distinguished scientist tells you that something is possible, he is almost certainly right. But if he says that it's impossible, he is very probably wrong. Arthur C. Clarke. I always like that quote. Kahn writes, suppose we insisted upon perfection and found it. A machine whose every arithmetic function rounds correctly to within half an ULP, that's unit in the last place. That's feasible for algebraic functions, but impractical for, he thinks it's impossible for exponential, logarithmic, trigonometric, and inverse trigonometric functions. And I did a search for Gustafson meme because I was looking for grumpy old men humor, but I was very surprised when the very first thing that came up was this. Kahn versus my attitude. It is absolutely possible to come up with a machine and a system where every floating point, or I should say every real number operation produces exactly the same result every time. You just have to change the rules that we're currently operating under. Here are what I call the design principles for format design. And I want to shout out to Laszlo Hunhold, who I see here online, for helping me sort these from most important to least important. The first thing is the distribution of representable values should closely resemble the distribution you need for exact calculations. That means every bit counts, but it also means every bit pattern counts. If you have a whole bunch of bit patterns that you never use, that's a huge inefficiency. There should be no redundant bit patterns. That means that what they mean. That means that there's no different, like 2 different kinds of 0 or lots of different ways to represent not a number. There are no hidden modes of operation. The source program and the data are sufficient to determine every bit of the output. You should not have to look at a make file. You should not have to know something about the condition of the machine or how it's been set up. You should be able to see it from the program and the data, just like you do with integers. All math operations must be correctly rounded. Kahn was claiming it was expensive. It is not expensive. It is very easy and fast to make all the math operations correctly rounded. It should be easy to change precisions like it is for integers, because we need to be able to do that. The error results, if you get something like a not a number or a not a real, then it has to always propagate through to the final output. So you are always warned that something went off the rails at the end, because you don't look at flags inside of a machine. No one does that. No one uses a debugger to look at condition flags. They just look, did it look like it hit infinity? Did it give me an error, an indefinite answer, an indeterminate answer? Now, here's some more. I had to split it across slides, but 7 is it should be simple to build in hardware and fast per watt. If you get fast per watt, that's the same as being fast, because we're all watt limited now. And that's what really this working group is about, right? So if you increase the operations per second per watt, you will also be able to build faster machines. Now, in the nice to have category, but still a good goal, it should be easy to scale to any number of bits, any number. Real numbers should be ordered like integers with the same, that is, if you map things to 2's complement, they have the same ordering. Then you don't need any extra hardware for comparison operations. That takes several percent out of the chip area for the floating point, the real number unit. Now, negating a real should be the same as negating it as an integer, and that's another simplification. The results of application computations should be close to what they would be if you had infinite precision. That's a more squishy one to evaluate. But now you've got 11 engineering goals laid out, and you can start to think about the trade-offs of emphasizing one over another, although most of these don't actually compete with each other. Some of them do. Trying to get more accuracy on number 11 is going to cost you in some of the others. But have you ever seen anyone lay out the goals of a real number format before as engineering goals? I'm pretty familiar with the literature. I've never seen this done before, but it's the very first thing you should do in any engineering project is lay out what are your goals. Anyway, IEEE standard 754 happens to fail every single one of these goals. If you go through it, it didn't get any of them right. Okay, so I introduced posits on Groundhog Day in 2017 at Stanford, giving a seminar. They have a seminar series, and these EE380 seminars are usually put on YouTube after each one, and they get about 300 views. I just checked, and this talk got 29,900 views. It's about to cross the 30,000 mark, and it's still rising. And near the end, Dr. Isaac Yonemoto, who is really a cancer researcher, not a mathematician, but he's a polymath, let me tell you. He did a live demo of successful machine learning using 8-bit posits. He did it right on the spot. So the last half hour is him fooling with the 8-bit posits, because as soon as he saw this format, he told me, you know, these would be perfect for machine learning and inference. This is what you need for AI. I didn't know that much about machine learning, but I later found out he was exactly right. So the revolution is underway. These are getting adopted like crazy. And there's Caligo technology over there on the left. I want to point that out because that's the people actually selling hardware and software stack and like a complete system ready to run. But University of Oxford is also kind of new on this splash because they're using it for weather modeling. They're using posits there. Huawei is using posits for their G5 network, and Bosch is putting them into some commercial products. But it's just exploding. The original paper, just a 16-page paper on posits, has like 470 citations now. So this is all the kind of things that are going on. And I won't go through these, but you can see that there's plenty of activity going on everywhere. There have been other attempts to introduce new number formats to replace floats, but none of them have caught fire. This one seems to be, has a life, has finally taken on a life of its own. So here's what reals I think we should seek to represent in terms of magnitude. So this is a logarithmic scale on the x-axis. And the typical distribution of real values used in computation almost never goes outside 10 to the minus 13th. And the central limit theorem kind of says that exponents should distribute as a bell curve. There's some logic behind this, but we've observed this empirically at a number of studies. Sometimes it's skewed. Sometimes there's more negative numbers than there are on the high side. You can often bound how big things get because overflow is disaster, but underflow is often quite harmless. So most of the classical algorithms are tolerant of underflow, but not so much overflow. Here's what IEEE gives you. Now look at all those bit patterns and look what a tiny fraction are actually used in computations. That's waste. And waste is, of course, waste of energy, waste of power. You got 83 decades of dynamic range for 32 bits. And I can't even show you the 64-bit floats where the exponent range is even sillier. 631 decades. I think Laszlo calculated that was like 2% efficiency in terms of only 2% of all the bit patterns in 64-bit IEEE are ever going to get used in real calculations. That is flat accuracy over a huge range really what we need? It certainly isn't. What you want is something that ramps down and has a sweet spot right near the most common numbers. And we call it the golden zone, where you have equal or superior answer accuracy to floats. So this is posit accuracy is a function of all the posits ranked from smallest to largest. But this is just one of the advantages of posits. They can have a bigger dynamic range and yet have higher accuracy at the same time. But they are much better matched to a Gaussian distribution like that. And you can adjust the slope of this accuracy. There's some parameters that let you tune it. How fast does it go down? You can also clip it off so it doesn't keep on going, but you get more accurate bits instead of tapering all the way down to no accuracy. So you get better accuracy with fewer bits, you get repeatability, portability, and it's a clean mathematical design. And what I found is that 32-bit posits can often replace 64-bit floats for high-performance computing, like scientific simulations. 16-bit posits can often replace 32-bit floats for things like signal processing, and 8-bit posits can replace 16-bit floats for artificial intelligence, both inference and machine learning. So that's a big savings of energy and power. Now, changing over to a new number format is going to be a revolution. It's like parallel computing. Parallelizing is a lot of work, but the change will be worth it. Now, I have to put this in because I think it's an important idea. It's in the book that I've written about this, but it's about energy and power. So I really figured I had to present this to you. This is a 400-year-old idea of John Napier, who actually invented logarithms. The word logarithm comes from logic and arithmetic, by the way. The tedium of using chalkboard methods for actually finding every digit were just so impractical if you had more than like 3 digits. But instead, you look up 1.23 in a logarithmic table and look up 4.56, where you shift the decimal point to make it between 1 and 10 in a logarithm table. You add the logarithms. Then you look up the anti-logarithm by saying, well, what x has that as its logarithm? But all of this involves rounding error. These logarithms are approximate. The result is approximate. The inverse is approximate. And so you only get something like 5.61 instead of 5.6088. So what if I told you the log method can be exact? I like memes. You find that out about me. Well, look at this. I'll take a set of real numbers. These happen to be the positive 4-bit or 5-bit posits. And so from 1/4 to 4, but with a few strange numbers that are not powers of 2, like 3/4 and 3/2 thrown in, that's the multiplication table. Look over there on the right. The addition table for the integers 0, 3, 5, 6, 8, 9, and 12 produces exactly the same ranking, which means I can make a lookup table or something like a lookup table, call it a logarithm table, but the results are exact. The exact result can be done for plus, minus, times, divide, and x to the y, not just multiplication. So what do the circuits look like for just mapping a set of values to a set of integers, adding them, and then mapping them back to a number? It looks like that. I mean, this is the actual circuit for the set of integers I just showed you. And you can do it in 13 gates to map 7 input posits to their 4-bit table values, add them, and then a similar circuit to map them back. So what's the logic delay? Well, you have to go through an AND gate, which might have a fairly large fan in, and you have to go through an OR gate to get the number out. Then you go through an n-bit adder, and then you go through this same circuit. So you're faced with like 4 logic delays plus the time it takes to add. That's a fraction of a clock cycle. So for small numbers, I can do plus, minus, times, divide, and power in less than a clock cycle. And that just blows away what you can do with FP4 and FP8 and things like that. For low precision machine learning, it looks to me like a far, far superior energy efficient solution. There's something called the quire as part of the Posit package, which reduces the need to use double precision or higher precision. Every n-bit Posit environment has a fixed point accumulator that has 16 n bits, probably just 1. All you need is 1. And then you can do exact dot products. And there's no possibility of overflow until you get beyond 2 billion long. So if you can do exact dot products, you can also do exact sums and even longer. And it's not humanly possible to get 10 to the 45th operations. That's length of the universe, stuff like that. But if you can do that, now you can do your adds in any order and not worry about associative arithmetic accumulation. And you can parallelize codes and get the same answer every time. Linear algebra is not only more accurate, it will give you reproducible, identical answers. You can multiply two matrices and have only one rounding error at the end in every entry. So an awful lot of singular matrix misbehavior goes away. And you just think of it as a vector of 16 integers. People are scared by the size of it, the thought of a 512-bit fixed point number. But if you just think of that as a sequence of integers, Berkeley has shown that the hardware can be quite fast. You can do multiply, accumulate in one clock cycle with this. Remember, when you're doing fixed point, you don't have to do things like rounding. You don't have to align fraction points and things like that, the radix point like you would have to do otherwise. So most of the reason programmers reach for high precision, double precision, is because they're afraid of the sums and they're afraid of the dot products being approximate. But if you have this quire and you use it, then those needs go away. So I really have yet to see a 64-bit high performance computing application that I can't do with 32-bit posits. Here's a challenging example, the dreaded Hilbert matrix. This is a matrix that is, it should be well behaved because it's symmetric, positive, definite, but it's not. It's got a huge condition number. Now, first of all, I have to scale it so that all of those fractions can be represented as base 2 numbers, as integer times 2 to an integer. So I scale it by 315 and then try to solve for the inverse. The inverse happens to have a closed form and it should all be integers. So let's see what happens when we try it with, let's see, I think I used 32-bit floats and 32-bit posits. The float result only gets 3 or 4 decimals correct because it's so ill-conditioned. If you do it with posits, you get 6 or 7 decimals, which is 400 times as accurate. But it gets better because with the quire able to do an exact dot product, you can now plug in this inverse, actually compute the matrix times this inverse with only one rounding error at the end and get a residual. You find out how off were you. Sort of like doing long division where you make a guess for what the divisor is, and then you do the multiply and you find you need a correction factor. That's how this works. So with the quire, the exact dot product, you can correct it and get infinite accuracy. You can actually land on every single integer that should be in the answers. Floats cannot do this even using double precision, even using quad precision. You can't. You have to have an exact dot product, not an approximate one. It's a secret weapon of posits. Now, 16-bit formats that have been tested for deep learning, the brain float or bfloat 16 from Google is 8 exponent bits followed by, it's proposed by Google, 7 fraction bits. There's IEEE 16, which people try to use for machine learning once and then probably don't ever try it again because it doesn't have enough dynamic range, which is why the brain float was invented. So you can correct IEEE 16 to say, well, let's pretend it had 6 exponent bits instead, but otherwise follow the rules. Now, if you could keep going and even have a larger dynamic range with 7 bits of exponent, but of course now you're starting to get very low accuracy in the fraction and what machine learning people call quantization error. It's just rounding error. Why do they have to make up a new name for rounding error? They call it quantization error. There's DL float from IBM, which proposes 16 bits for the exponent and also fixes a lot of the rounding rules to make it more economical and gets rid of the duplicate nans and not a number representation and all the other junk. They kind of cleaned up IEEE, and that works actually pretty well, we'll see. But then there's posits with various number of exponent bits. I didn't get into the exponent bits, but you can read about that in the paper or the book. It's a way of adjusting the dynamic range. But anyway, here's the distribution of values needed for AI, say, in a typical run. And as I say, it's skewed. The values almost never get larger than 10, let's say for the weights or the activations or the gradients, but they can be quite small. But so it's a kind of a Gaussian distribution, but a little bit clipped on the right. So you can match that distribution with posits almost perfectly with all the different parameters that you can adjust and make sure that the vocabulary of numbers that you need is almost exactly the vocabulary of numbers that you can represent with binary. And that's more information per bit. So we tried things out with all these different 16-bit formats for various things like CFAR 110 and ImageNet, and, the standard benchmarks. And as I say, IEEE, it does some pretty disastrous things. It either produces NaN, you can get the 0 divided by 0. rather easily, or it gets none of them right, even though it should be able to guess just randomly, should be able to do better than 0%. And that also happens even with IEEE 7. But if you do use 6-bit IEEE, it sort of works. It comes close to working for 16 bits. And DL float does a respectable job too, but the Posit 16 standard does well all across the board. And even using 3 bits, you can actually beat the accuracy of 32-bit, the gold standard. It's absolutely remarkable how much better a 16-bit Posit can do than using 32-bit floats. Now let's see, there's 8-bit Posits. We've used those to train MNIST, which is kind of a toy machine learning benchmark, recognize handwritten numerals between 0 and 9, but very respectable accuracy. And these things like E-bias and RS, these are other parameters that can be adjusted to tweak the Posit format while preserving that idea of mapping to the projective reals. Here's what you get with a generative adversarial network of various precisions. The top row is trying to enhance resolution of a low resolution picture of a monarch butterfly. And FP16 does pretty good, but you can get all the way down to an 8-bit Posit. If you try using an 8-bit floating point, you get garbage. The horse to zebra is an interesting challenge. You got to get the stripes oriented correctly, and a 32-bit does a nice job of that. 16-bit floats, it looks kind of wonky on the belly of that zebra. It didn't figure out how to get them oriented up and down. And by the time Posit seems to get that right, if you try using FP8, it turns everything into a zebra. It turns the mountains and the dirt and everything else into zebras. The DC GAN is come up with a fictional bedroom set and make a picture of it. So that can be done, again, with 8-bit Posits, but not with floating point 8. So we found out we couldn't get anything out of generative adversarial networks with 8-bit Posits, with 8-bit floats, but we could with Posits. Now, this is a little confusing because in the case of some of these, lower score is better, and the other, for the EarthScan one, the bedroom set, higher is better. But you can see that a modified Posit does an extremely high score for generative adversarial networks. Weather climate modeling with 16-bit Posits shows that the 16-bit Posit with one exponent of it does much better than a 16-bit float for discretization error, and they've got the perfect forecast there. Lawrence Livermore, Peter Lindstrom did an independent study very early in the history of Posits, and he concluded that Posits were 2 orders of magnitude more accurate than floats in a study that he did of shock hydrodynamics using these things. So I think 32-bit precision may suffice now for HPC. The very early computers, before the System 360 came out, were 36 bits. Now, byte was 6 bits, really ancient times here. But the 36-bit float is actually just about the point where if you do it right, you can handle most scientific calculations. When they went to 32-bit, and they did it rather badly, the floats were not accurate enough. And that forced everybody to start using 64-bit double precision for everything. But what if 32-bit Posits could replace 64-bit for structural analysis and circuit simulation and computational chemistry and all these other codes? That would be a godsend. God, could we could go so much faster. That's at least 4x energy of savings, because now you're going twice as fast because you're using lower precision, but you're also moving half as many bits, and you also get cache effects because now more things fit into this L1, L2, and L3 cache. You're making better use of the caches, so that's why you get more than 4x speed up. So if I go to those principles of computer arithmetic and look through them again for Posits, I can now match the distribution. There's no redundant bit patterns. Every bit pattern represents a different quantity. There are no hidden modes of operation. All math operations have to be correctly rounded, and they are. And it is very easy to change precisions. All you do is tack on 0 bits to increase precision or round them off to decrease precision. It's just like integers. The error results must always propagate. The way positive arithmetic works, if you hit that NAR, it always propagates. It should be simple to build in hardware and fast. Well, that's proved to be true. It is slightly more complicated, but you get so much more accuracy that it's not fair to say, well, a 32-bit Posit circuit is 10% larger than a float circuit. I say, well, yeah, but we could replace a 64-bit circuit with a 32-bit circuit, and that's way smaller. In the nice-to-have category, it is easy to scale to any number of bits. In fact, you can have 3-bit Posits, 4-bit Posits, 5-bit Posits, and that's hard to do with floating point. Real numbers should be ordered like integers. Yes, they are. So you don't need a comparison unit. And negating, of course, works perfectly. Just negate it and treat it as an integer bit string. The results of application computations are closer than they are. Of course, this is an infinitely hard goal to make infinite accuracy. So as I say, this is the squishy goal, but they do a better job of getting accurate answers. It's an improvement. So here's the shameless plug. The book is the same as the title of this talk, Every Bit Counts, Posit Computing. 9 years in the making. And this is the publisher, CRC Press, very generously allowed me to put all 464 pages in full color. And I have a copious number of illustrations and diagrams, plus a lot of humor. This is not like any other math book you've ever read. It's full of cartoons and memes and anything I can do to get the point across as easily and simply as possible. I used Einstein's test. If you can explain it to your grandmother, then you understand it. Otherwise, you don't. I actually had a grandmother read it. I think we have a grandmother on the call here. So we'll see if she gets it after this. But I tried to make it as clear as possible and not use any calculus, not use any higher math. To the extent that I bring in linear algebra, I explain linear algebra from first principles and in a way you probably haven't seen it taught before. So in summary, better answers, fewer bits. We can get bitwise reproducibility for real number programs. That can be done for the first time. And boy, if we needed that. Low precision posits work really well for AI apps. NVIDIA seems to be hoping that posits will go away. They just will. They don't want to do the wrenching change to start thinking about a completely different way than this is the exponent field, this is the fraction field, this is the sign bit. They just can't get their head around it. Posit adoption really has caught fire, especially for RISC-V. And RISC-V, it was Kurt Kebbel who asked me 8 years ago, we need a number format for RISC-V, and we don't want it to be IEEE floats. And so that's when I came up with the Posit number format. And so I'm grateful to him for pushing me over the edge to finally design a hardware-friendly alternative. So this allows you to use smaller precisions to achieve acceptable accuracy. And that is an obvious savings. So thank you. For more information, you can go to posithub.org, or you can buy that book I just held up that I just showed you. Now I think we go into the Ask Me Anything section, right?
Yeah, thank you, Mr. Gustafson, for that incredible presentation on posit computing. It's clear that this work has the potential to redefine the efficiency in HPC. And I know that many of us are eager to dive deeper. So to our audience, if they have any questions, now it's your chance to ask. Please submit them in the panel and we'll address them as the time allows. To kick things off, I actually had a question myself. One of the most striking points that you raised is how posit computing reduces energy waste in calculations. So I was curious to know, could you share a practical example of where this could make the biggest impact in real world HPC applications?
Well, think of all the signal processing that is done. It is almost all done with 32-bit numbers right now. They try to use 16-bit IEEE floats, and it's not enough. It loses so many decibels of signal to noise ratio that you can't do it. I tried using with a 12-bit A to D converter, you get obviously 12 bits of accuracy. And if I do Fourier transforms and standard signal processing filters on that with posits, I can do absolutely perfect answers that it's like if I do a forward Fourier transform and an inverse Fourier transform, I get back the exact set of 12 bits that I started with. So it's lossless, and floats cannot do that. So imagine that everything we do with signal and image processing worldwide, we're converted to half as many bits as it is now. And imagine that the dynamic range of sound and images naturally map to the dynamic range that you can actually hear and see. Your eye can go like 14 orders of magnitude. Your ear can go for 14 orders of magnitude instead of the fixed point range. So it kind of revolutionizes that human to computer interface to be able to deal with a dynamic range of real numbers and still get useful answers and not have to go through this layer of odd integer truncation, approximation, scaling stuff. So that's by itself kind of revolutionary, I think. I hope that answers your question. But I think one of the low-hanging fruits is signal and image processing, because those don't necessarily have to be able to trade the format with other devices. They just have to work locally.
I see. Fantastic. Thank you.
Mhm.
We have a question coming from our audience. Terry
Yeah,
White is
yeah.
asking. Yeah.
You mentioned posit.org. What is the URL for it?
Posithub.org, you say?
Which one? You said there is a website where you can get more information.
Yes, posithub.org.
Posit, can you put it in the chat, please?
There's a there's the posit standard is there. There are tools for, let's say, converting numbers to posits and back, demonstration calculators. There are some pointers to papers on the subject, and there's a lot of stuff there. There's some of the conferences that have been held on posit computing. It's called the annual conference is called the Conference on Next Generation Arithmetic, and or CONGA, CONGA. And we are just about to put out the call for the papers for the one that's going to be held as a workshop attached to the supercomputing conference in November. We had been holding it under SC Asia, and the proceedings are published by Springer, but will continue to do that. But there's a lot of refereed papers in the 5 years that we've held the Conga conference that are useful, and I think we have material put up on the posithub.org. We're kind of polishing up that site now. Kurt Kevel has taken over the site and is making it much better. It's been poorly maintained until recently.
Excellent.
Everything's free, by the way. There's no cost to any of this software.
But the book is not, your book is not free.
The book is certainly not free. It is for being full color. It's inexpensive, but as books goes, there are discounts to get it down to about $45. But I'm sorry, it's such an expensive book.
So Natalie sent me an email about energy consumption.
You said you're sending an email about energy consumption?
Yeah, she sent an email to me about working with LBL on energy stuff.
Yes, I'll reply to you. I haven't yet done that, but thank you. I think Hisham, I think we have some other people who are asking questions, so I'm going to turn
Okay,
to Trey.
Okay, no problem.
I do not have a hard stop at the hour mark. I can keep on going if you can.
We can go for a few more minutes. We do have a question from Trey and another one from Nicholson.
Trey?
Sorry, I put it in the chat. Yeah, taper precision can lead to multiplicative cancellation. How serious of an issue is that? And are there mitigation strategies if you're a user of posits?
Yeah, in the as you read in the book on the Every Bit Counts book, the mitigation strategy is to limit the size of the regime to like 6 bits. And that means that you always have a fairly large number of fraction bits. Instead of tapering all the way down to 0, it looks like a tenth and it stops. And you still have plenty of dynamic range, but you always have at least 6 bits of fraction significance. So that you can blunt this triangle shape, and that helps a lot. Yes, there are situations where you can get some problems with the very large magnitude and very small magnitude numbers producing rounding error, but there are mitigation strategies for that. And mostly it consists of blunting the dynamic range, which raises the accuracy. What's the other next question?
Okay, thank you.
We also have another question from Nicholson Cook Paisan. They ask, 32 and 16-bit posits provide similar accuracy to 64, 32-bit floats in practice. Have you tried 64-bit posits, and are there other trade-offs there?
The Caligo Technologies chip that I held up, this one, it has 64-bit and 32-bit posits. And the 64-bit posits, I think, are going to be very interesting for chemistry to compare. They actually have ported chemistry codes like GROMACS, and I think maybe NW Chem for quantum chemistry. And chemists are always looking for more accuracy. Even 15 decimals is sometimes not enough for them. So the fact that 64-bit posits have 128 times the accuracy of 64-bit IEEE floats. So I'm interested to see if this solves problems for people that they just couldn't get the right answers before, but now they can. So yes, we not only have we tried them, they're in VLSI.
Great, thank you.
I have another question too.
Mhm.
What kind of tools you would advise to the developers to port their applications from floating point to Posit computing to adapt them better?
Well, first of all, there are software simulators from various places of posits, and so you don't have to have hardware at all. You can the float simulator from Berkeley is called Soft Float, and we made a perfect we mapped that to Soft Posit, and that's a freely available thing on GitLab. So there's also a universal library from Stillwater Supercomputing, which is also free, which does all kinds of variations on the Posit format and supports it. And there are tools that go with these. I wouldn't say we have an interactive development environment equivalent to what we have now for other codes, but I think what Caligo has is a rather complete debugger, development, all the things you would expect in a normal programming development environment are available for posits from Caligo. I hope to see other groups also supporting it as a tool set.
I see. Thank you. I guess we don't have any more questions from our audience.
That's perfect.
We are just on time. Thank you for the presentation. Thank you for answering our questions. That was fantastic.
My pleasure. So long, everyone.